Good morning, everyone. Also, warm welcome from my side to the webinar today with the topic Market Update on Bio-based Building Blocks and Polymers. And before we start with the main part of this webinar, a short introduction to the nova-Institut. Nova was founded about 30 years ago and has a multidisciplinary and international team of nearly 50 scientists that are focused on the science-based consultancy on renewable carbon for chemicals and materials. And we have 4 departments in total, a communications department where my colleague Anke is a part of. We also have a sustainability department focused, among other topics, on life cycle assessments. We also have economy and policy department and a technology and markets department where I am a part of. And here we are focused, among other topics, on market research, innovation, and technology scouting, as well as the setup of customized expert workshops. And we also create and published dedicated market and trend reports, mainly focused on bio and CO2-based building blocks, chemicals, and polymers, and also on chemical recycling, or as we called it, advanced recycling. And today I will present you the results of our most recent report that is focused on bio-based building blocks and polymers. As you may all know, there's a large variety of bio-based building blocks and polymers out there currently on different scales, ranging from lab already to commercial scale, that are produced from different kinds of bio-based feedstocks. And the bio-based building blocks and polymers that are already on demonstration or commercial scale are highlighted here in bold. And all of these bio-based building blocks and polymers are covered in our report. So we have 16 bio-based building blocks already on demonstration or commercial scale and 17 bio-based polymers. And in general, all of these bio-based building blocks and polymers can be classified into 3 different groups: drop-in, smart drop-in, and dedicated bio-based chemicals and polymers. Drop-ins are chemically identical to their fossil-based counterpart and undergo the same production process based on bio-based feedstocks. So the production process is completely identical to the production process of the fossil-based counterpart. So you just switch the feedstock from fossil-based to bio-based, and the production process stays the same. Smart drop-ins, on the other hand, even though they are chemically identical to their fossil-based counterparts, show different advantages when it comes to their production process. For example, producing these smart drop-ins from bio-based feedstocks result in less energy demand or less energy use during the production process. The time to product is shorter.
Yeah, sorry, I need to interrupt you because we have a problem here. It seems that the slides are not very clearly, so they seem to be blurry. Maybe it's your internet connection.
I don't know.
Now it's better.
Okay.
Thanks. Sorry for interrupting.
Okay, no, it's fine. So smart drop-in production process. So the second advantage is that the time to product is shorter due to less complex or shorter production pathways. And the third advantage is that you use less toxic or harsh chemicals during the production process. An example for this are epoxy resins based on bio-based epichlorohydrin. So in the conventional production process, the epichlorohydrin is produced from fossil-based propylene that is then converted in a 3-step process using toxic chlorine into epichlorohydrin. And when you use glycerol as a bio-based feedstock, you only have a 2-step process and you do not use the toxic chlorine in this production process. And last but not least, we have the dedicated bio-based chemicals and polymers. And these building blocks and polymers do not have a fossil-based counterpart. They are only available from bio-based feedstocks. And the examples are shown here. So we have cellulose acetate, for example, polyethylene furanoate, polyhydroxyalkanoates, polylactic acid, or also bio-based polyurethanes that are based on natural oil polyols and starch-containing polymer compounds. So let's start with the market update on the bio-based building blocks. In 2023, we had a total production capacity of these 16 bio-based building blocks of 5.3 million tons. And this capacity is expected to increase to 11 million tons in 2028. So this reflects a compound annual growth rate for these 16 bio-based building blocks of 16%. If we look on the development in the capacities from 2022 to 2023, the capacity increased of about 1 million tons. And the main drivers for these capacity increase were worldwide expansions for lactic acid capacity, as well as for bio-based naphtha. We also had an Asian expansion in the production capacity for bio-based epichlorohydrin, as well as a worldwide expansion for bio-based ethylene. When it comes to the development to 2028, as I already said, we will increase, or it is expected that we increase capacities of over 11 million tons in 2028. And the main drivers until 2028 are 1.5 pentamethylene diamine that is mainly used for the production of polyamides. Also, we will have a capacity expansion for succinic acid, as well as 1.4 butanediol for the different furan derivatives, as well as lactic acid and monopropylene glycol. So if we have now a closer look on the furan derivatives, so we cover these 4 furan derivatives in our report. So 5-chloromethylfurfural, 2.5 furandicarboxylic acid, furandicarboxylic acid methyl ester, as well as 5-hydroxymethylfurfural. And these 4 furan derivatives in total had a capacity of 18,000 tons in 2023, and the capacity is expected to increase to 700,000 tons in 2028. The main drivers for capacity increase from 2022 to 2023 were capacity expansions for 5-chloromethylfurfural, mainly in North America and Australia, an increase of the capacity of 5-hydroxymethylfurfural, mainly in Asia, as well as capacity increase of FDCA, also mainly in Asia. When it comes to the increase of the expected increase in the capacity to 2028, we see expansions in FDCA production capacity, mainly in North America, as well as for 5-chloromethylfurfural and for 5-hydroxymethylfurfural. We expect a capacity increase until 2028, mainly in Asia. For FDME, currently this is produced in Asia at the moment, but the production capacities that are installed currently are not disclosed at the moment. So we expect this is at maybe demonstration or already at commercial scale, but we do not know for sure. So now we come to the bio-based polymers and their capacities and production. And if we have a look at the total plastics production worldwide in 2022, we had plastics production of 386 million tons in 2022, whereby 4 million tons were made up by bio-based plastics, which reflects about 1% of the total plastic production worldwide in 2022. If we look at this a little bit more diversified, so not only including plastics itself, that are covered here under functional and structural polymers, but also extend this to rubber products and man-made fibers, we had an overall worldwide production of all of these polymers of over 500 million tons, whereby 8% were made up from bio-based polymers. Man-made fibers with nearly 88 million tons in total, and a little bit more than 7 million tons were bio-based man-made fibers. Rubber products had a share of 15% when it comes to bio-based rubber. And here in the field of functional and structural polymers, we have a bio-based share of 5%. And if we now look into the split, so we have for the functional polymers almost 30 million tons in total, so fossil and bio-based, whereby 47% are coming from bio-based functional polymers. And here on the other side, we have bio-based structural polymers with 4.5 million tons, so reflecting 1% share of the total volume of structural polymers being produced. And these 4.5 million tons are split into 100,000 tons coming from bio-based linoleum and 4.4 million tons coming from the bio-based structural polymers. And this is then splitted here. So the majority is coming from cellulose acetate and epoxy resin. You will see it later a little bit more in detail on another slide. So yeah, 4.4 million tons of bio-based polymers being produced in 2023, and 4 million tons were produced in 2022. I think the most of you are familiar also with the production capacities for bio-based polymers that are annually published by European Bioplastics. And European Bioplastics received the data from us for the bio-based polymer production capacities. So the volumes for the individual polymers and their capacities are exactly the same for us and for European Bioplastics. But the total volume, as you can see here, differs. And this is due to the fact that European Bioplastics has a different scope. So European Bioplastics data does not include aliphatic polycarbonates, cellulose acetate, epoxy resins, EPDM, and they also do not include polyurethanes. So they have a different scope in the polymers that they are shown in their production capacities, and therefore we have a difference in the total overall volume. So bio-based polymer production capacities in 2023 were at 4.8 million tons, and they are expected to increase to over 10 million tons in 2028 for these 17 bio-based polymers. So this reflects then a compound annual growth rate of 17%. The main drivers for the capacity increase of about 500,000 tons from 2022 to 2023 were an Asian expansion for polylactic acid as well as for polyamide production capacities. We also saw an Asian expansion for the production of epoxy resins, a South American capacity increase for polyethylene, as well as a worldwide capacity increase for the production of polyhydroxyalkanoates. When it comes to the forecast to 2028, so the overall capacity is expected to increase to 10.5 million tons. And the main drivers here are also polylactic acid in Asia, as well as polyamide in Asia. And we also have a worldwide expansion until 2028 for the capacity of polyhydroxyalkanoates, a North American capacity increase for polypropylene, and also an Asian expansion for epoxy resin production. So these were the production capacities for the bio-based polymers in 2023. And when it comes to the actual production, we had an actual production of 4.4 million tons in 2023. And the major share of these bio-based polymers produced were coming from cellulose acetate and epoxy resins, altogether making up over the half of the bio-based polymers produced in 2023, followed by polylactic acid with a share of 11%, 100% bio-based. Then we had an 8% share in the production for polyamides that are on the average have a bio-based content of 60%, polyurethanes with a 7% share on the production, and polyethylene that is available 100% bio-based and also 30% bio-based, and poly-3-methylene terephthalate with a bio-based content of 30%. They had a share of 6% and 5% from the total production volume in 2023. And the bio-based polymers PBAT, PET, polyhydroxyalkanoates, and the starch-containing polymer compounds had a share in the production that was below 5%. And you may have noticed that we do not have shown here all of the 17 bio-based polymers, and this is due to the fact that aliphatic polycarbonates, casein polymers, EPDM, PBS, polyethylene furanoate, and polypropylene had a share on the worldwide bio-based polymer production less than 1%, and therefore they are not shown here in this overview graphic. When it comes to biodegradability of polymers, it is necessary to know that the biodegradability of polymers is completely independent from the resource the polymer is made of. So this means being bio-based does not necessarily implement a biodegradability of the polymer. And the biodegradability is dependent on the specific grade of the polymer. So the overall final product is tested for biodegradability, and this does not include the polymer itself, but also additives and fillers that have to be proven for biodegradability. And of course, the biodegradability is tested according to the conditions that are defined in certification schemes and in the standards. And good examples for showing the complexity of biodegradability are PBS and its copolymers, as well as PBAT. So PBS as an example, PBS and PBSA are both industrial compostable, but only the PBSA biodegrades also under home composting conditions and in soil. And another example is PBAT. So PBAT is industrial compostable, as you can see here, and for certain grades also biodegrades under home composting conditions as well as in soil. And this biodegradability for PBSA, its copolymers, and for PBAT is true for bio-based PBS and PBAT, as well as for fossil-based PBS and PBAT. So when we now have a look on these 10 non-biodegradable polymers that are covered in our report, we had an installed capacity of 2.7 million tons in 2023, and this volume is expected to increase to 4.9 million tons in 2028, so reflecting a compound annual growth rate of 13% for these 10 non-biodegradable bio-based polymers. So the significant findings from 2022 to 2023 saw a capacity increase of 200,000 tons. The main drivers for this capacity increase were, as I already mentioned, an Asian expansion for polyamides, as well as an Asian expansion for epoxy resin production, and of course, the capacity increase of polyethylene in South America. When it comes to the forecast to 2028, bio-based non-biodegradable polymer capacity will reach 4.9 million tons, or is expected to reach 4.9 million tons in 2028. And main drivers here, polyamide capacity increase in Asia, as well as in the capacity increase for polypropylene production in North America, and an Asian expansion for epoxy resins. So, bio-based biodegradable polymers, we have these 7 polymers here. And in 2023, we had an installed capacity of 2.1 million tons, and this is expected to increase to 5.7 million tons in 2028, and this reflects then the compound annual growth rate of 22%. So a far higher growth rate than it is expected for the non-biodegradable bio-based polymers. And also here, the capacity increase from 2022 to 2023 is based on 2 main drivers here: the Asian expansion for the polylactic acid capacity and the worldwide expansion for the polyhydroxyalkanoate capacity. And when it comes to the forecast, so the capacity expansion to 2028, also here the main drivers where we expect an increase in the capacities are polylactic acid in Asia and polyhydroxyalkanoates on a worldwide level. So if we have a look on polyethylene furanoate in 2023, we had an installed capacity of 50 tons, and this is expected to increase to 25,000 tons in 2028. And the main regions producing polyethylene furanoate or having installed capacities for polyethylene furanoate production were Europe and Asia. Of course, in Europe, Avantium in the Netherlands. And for 2028, we expect a far more installed capacity in Asia than in Europe when it comes to the production of polyethylene furanoate. So these were the capacities and production for the bio-based polymers, and now we will have a look on the regional split as well as on the market applications for the 17 bio-based building blocks. And in 2023, the largest region having installed production capacities for bio-based polymers was Asia with 55%, with the largest capacities installed for polylactic acid and polyamides, followed with 19% for North America, mainly based on polylactic acid production and polytrimethylene terephthalate production. South America with 13%, mainly based on polyethylene, and also Europe with 13%, mainly based on installed capacities for starch-containing polymer compounds and polyamides, and with less than 1%, we have Australia and Oceania, where mainly starch-containing polymer compounds are being produced. And with an expected compound annual growth rate of 35% between 2023 and 2028, Asia displays the highest growth of bio-based polymer production capacities compared to the other regions in the world. And this capacity increase in Asia from 2023 to 2028 is mainly based on the higher production capacities for polyamides, polyhydroxyalkanoates, and polylactic acid. So when it comes to the shares of the produced bio-based polymers in different market segments in 2023, fibres had the largest share with 27%, mainly based on cellulose acetate and polytrimethylene terephthalate that are being used for fiber production, followed by packaging, flexible and rigid with 21%. Then we have the functional applications with 17%, automotive and transport with 10%, consumer goods that includes, for example, coffee capsules, bio-waste bags, leisure and interior with 9%, building and construction with 6%, 5% going into electrics and electronics, and 2% each for agriculture and horticulture applications, as well as for other applications. And these other applications includes films that are not used in agriculture and horticulture, 3D printing, medical applications, as well as aquaculture. So, biomass utilization. How much biomass do we need for the production of the bio-based polymers? So the total demand for biomass worldwide, with the reference years from 2021 to 2023, was 13.5 billion tons, where the majority, with 56%, is used for feed production, 16% for bioenergy, 15% for food, 11% for material use. That includes also wood applications or wood-based products. 2% are going into biofuels, and only 0.029% of this worldwide biomass are used for the production of bio-based polymers. So this reflects 3.9 million tons of biomass feedstocks that are used to produce the already mentioned 4.4 million tons of bio-based polymers. And the share of the 3.9 million tons of biomass feedstocks used are shown here. So we have 28% of the biomass coming, or the bio-based feedstock coming from sugars, 25% from glycerol, that is a byproduct for biodiesel production, 24% is starch, 12% non-edible plant oil, with the majority being castor oil. Then we have 7% that are coming from cellulose, mainly for the use of cellulose acetate, and 4% from edible plant oils. So everything that I have shown you in brief on the slides before is covered in more detail here in our bio-based building blocks and polymers report on a total of over 400 pages. So we have the data for 2023 and the forecast from to 2028 for the 16 bio-based building blocks and the 70 polymers. We also have a statistical report on mass balance and free attribution products available worldwide that is based on an extensive analysis of the ISCC database. And this report also includes a detailed elaboration on the current European policy for bio-based polymers. And we also include in this issue a comprehensive summary on the biodegradability and biodegradable of polymers. So and also we include over 230 company profiles from the companies that are producing the bio-based building blocks and polymers. And you can purchase, if you want, the report here via this link, but you can also find here a freely available short version of the report where you can have a look inside and check the table of content and see what is all included in this report. And last but not least, I would like to draw your attention to our Renewable Materials Conference in June this year, 3 days in Siegburg. And these 3 days are focused on all of the 3 feedstocks for renewable carbon. So we have dedicated sessions on bio-based building blocks and polymers, as well as on carbon capture and utilization, and also dedicated sessions on chemical recycling, or as we call it, advanced recycling. So yeah, and with this, I would like to thank you for your attention, and I'm happy to take your questions.